You know those super strong alloys in a jet engine, or the crazy lightweight composites in a race car? Ever wonder how we actually designed them? For centuries, it was pretty much just educated guesswork, a lot of trial and error. But today? Well, today, we can build these things atom by atom, inside a computer, before we even touch a real lab. So yeah, let's dive right into this fascinating world of computational materials science, where we get to predict and design the future.
For the longest time, material science was, a very linear game. You'd process something, take a look at its microstructure, measure its properties, and then finally see how it performs. And sure, it worked, but man, was it slow and expensive. The challenge we face now is that the real magic, the important stuff, happens across these unbelievable scales. From the way individual atoms talk to each other all the way up to how a whole airplane wing behaves. So the question is, how on earth do you connect something that happens at a picosecond to a product that needs to last for years?
Well, that massive challenge is exactly where the breakthrough happens. We needed a totally new way of seeing, a new way of predicting. What's so amazing about this is that it's not just one field, it's this powerful fusion. You take all the physical knowledge from material science and physics, you combine it with the universal language of mathematics, and then, this is the key, you use the raw power of numerical analysis to let a computer do all the heavy lifting. This lets us create what's basically a digital twin of a material, so we can poke it, prod it, and test it all virtually. And this really gets to the heart of it all. The whole point isn't just to make cool-looking computer models. It's about getting real predictive power. We want to understand why a material acts the way it does, to predict exactly how it's going to react under intense heat or stress, and, the ultimate goal, to design completely new materials with the precise properties we want right from scratch. Okay, so we know what we want to do, but there's a huge technical hurdle. How do you actually get a computer to understand the messy, chaotic rules of physics? It's a great question, isn't it? The universe just doesn't run on simple, clean equations that you can punch into a calculator. The reality of how atoms are bouncing around, how heat is flowing, or how a piece of metal bends, it's all incredibly complex. So this is the crucial point, this mathematical barrier. Most of the real-world stuff we care about, like plasticity or diffusion, is described by these things called nonlinear differential equations. Now, all you need to know for our purposes is that nonlinear is basically math speak for extremely difficult, and often totally impossible to solve perfectly with just a pen and paper. And here's the solution, and it's really brilliant: discretization. The idea is, if you can't solve the whole messy, continuous problem all at once, you just slice it up. You chop it into a huge number of tiny, simple little pieces that a computer can solve one by one. I mean, think about a digital photo, right? A smooth, real-life curve gets turned into a bunch of distinct pixels. But if you have enough pixels, it looks absolutely perfect. That exact idea is the foundation for some super powerful tools. You've got things like the finite element method, we call it FEM, which is amazing for modeling how whole structures bend and break. And then you have something like molecular dynamics, which literally simulates the chaotic dance of individual atoms. But here's the thing, materials are complex, and a one-size-fits-all approach just doesn't work. To really understand a material, you have to look at it on this whole hierarchical ladder of different scales. I mean, what's happening down at the electronic level with chemical bonds is a completely different world from what's happening at the macro scale, where you can see a bridge bending under a heavy load. And this whole system works because each rung on that ladder has its own special tool. Down at the tiniest electronic scale, we use methods like density functional theory to figure out the quantum glue holding chemical bonds together. Zoom out to the atomic scale, and you've got molecular dynamics tracking the movement of every single atom. And then, as we zoom way out to the big, visible macro scale, we use tools like continuum FEM to predict how a full-size part is going to perform under stress. It's a whole toolbox. Now, a common question I get is, does all this simulation mean we don't need real-world labs anymore? And the answer is a definite, resounding no. Actually, it's a perfect partnership. You get this incredible feedback loop going. See, experiments in the lab, they give us the hard data. That's our ground truth, right? It's what keeps our models honest. But here, and this is the real game changer, the simulations take that data and give it meaning. They let us explore, literally millions of potential materials, and the time it would take to physically test just one. It's a synergy that just completely changes the economics of discovery. Okay, this is all fantastic in theory, but where does the rubber meet the road? How is this stuff actually changing the way we make things in the real world? This is where it gets really exciting. Take traditional metal forming, like rolling steel. Simulations can predict exactly where stress is going to build up, helping engineers prevent super costly failures before they happen. Or think about the world of 3D printing, additive manufacturing. We can simulate the laser melting the metal powder, predicting the temperature and stress to make sure that the final part comes out absolutely flawless. We're moving from being reactive to being truly predictive.
So the whole process, from a simple idea to a powerful insight, follows this really clear, structured workflow. First, you have to formulate the physics into mathematical equations. Second, you do that all-important step we talked about, discretization, to turn it into something a computer can actually chew on. Third, the computer does its thing and solves millions of tiny equations. And finally, in post-processing, you turn all that raw data into beautiful visualizations so you can actually understand what it all means.
At the end of the day, mastering these tools, understanding the math, running the algorithms, and analyzing the results, that's what allows us to go beyond just explaining the materials we already have and start actually engineering the materials of tomorrow. It really just brings up one final fascinating question. Now that we have the power to design materials atom by atom, what incredible new inventions are waiting for us just around the corner?